This video discusses multiplexing. Multiplexing technique. Multiplexing technique is used in communications and input-output operations for transmitting a number of separate signals simultaneously over a single channel or line. This allows two or more signals to share the same medium or channel. This illustrates the multiplexing technique. For example, we have signal 1, signal 2, signal 3, up to signal n number of signals. It will all pass through a MUX. This is short for multiplexer. A multiplexer is a circuit that combines several signals, and its output is a single signal that comprises all the informations of all the signals in its input. So after all the signals passes through a MUX, it will be combined into one signal that will then be sent through a single path or a single channel to be received by the demux. The demux is the opposite of a mux. It's short for demultiplexer. A demultiplexer is a circuit that will then separate all of the signals which had been combined by the multiplexer. So the output of the multiplexer is every signal from signal 1 up until signal n that is the similar input of our multiplexer. So obviously, multiplexing is crucial if we want several transmitters and several receivers to communicate at the same time if we only have one line of path between them. An example for this is our household telephones. The central office for our telephone provider combines several signals from every telephone that is in operation. There are two major types of multiplexing technique. First is the analog. Under analog, we have FDM or frequency division multiplexing and WDM, that is wavelength division multiplexing. We also have digital multiplexing. In digital multiplexing, we use time division multiplexing. And time division multiplexing can be categorized into two more categories. First is the synchronous TDM, and second is the asynchronous TDM. All of these will be discussed in the slides to follow. Frequency division multiplexing. Frequency division multiplexing is the most used technique in analog multiplexing. It uses various frequencies to combine streams of data for sending them on a communication medium as a single signal. Wavelength division multiplexing. Wavelength division multiplexing is an analog technique in which many data streams of different wavelengths are transmitted in the light spectrum. If the wavelength increases, the frequency of the signal decreases. A prism which can turn different wavelengths into a single line can be used at the output of the MUX and input of the demux. Time division multiplexing. In time division multiplexing, the time frame is divided into slots. This is done to transmit several signals over a single communication channel by allotting one slot for each message. Code division multiplexing. This is a multiplexing technique that uses spread spectrum communication. In spread spectrum communications, a narrow band signal is spread over a larger band of frequency or across multiple channels via division. This does not constrict bandwidths, digital signals, or frequencies. This is less susceptible to interference, thus providing better data communication capability and a more secure private line. Now, let's take a look at multiplexing more closely. Multiplexing is a set of techniques that allows the simultaneous transmission of multiple signals across a single data link. This is done using a device called multiplexer or MUX that combine n input lines to generate one output line. At the receiving end, a device called the multiplexer or demux is used to separate signal into its component signals, i.e. one input and several outputs. Why do we want to multiplex? Well, bandwidth utilization is the wise use of available bandwidth to achieve specific goals. Efficiency can be achieved by multiplexing, i.e. sharing of the bandwidth between multiple users. Whenever the bandwidth of a medium linking two devices is greater than the bandwidth needs of the device, the link can be shared. Multiplexing is a set of techniques that allows the simultaneous transmission of multiple signals across a single data link. As data and telecommunications use increases, so does traffic. This is just the same illustration as before. As you can see, there are many signals that will serve as the input for the multiplexer. But the multiplexer will combine them into a single output that will pass through one link. So this one path can serve as multiple channels for our messages. Now the multiplexer does the opposite of the multiplexer. It separates one signal into multiple signals, which are the original message signals. No multiplexing versus multiplexing. In no multiplexing, we can only transmit and receive information between two devices, and one wire or one path is required to transmit or receive for each pair. If, for example, we want one device to transmit to other devices or multiple devices, we need to add separate wires or separate paths for the message to travel through. Unlike in multiplexing, we only need one path for the signal to travel through. And it also has the advantage of being able to send information to more devices at the same time without the need of multiple paths. Advantages of multiplexing. More than one signal can be sent over a single medium or link, and the effective use of bandwidth of a medium. Frequency division multiplexing. Signals of different frequencies are combined into a composite signal and is transmitted on the single link. Bandwidth of a link should be greater than the combined bandwidths of the various channels. An example for this is radio broadcasting. All the signals are transmitted over a single medium, which in broadcasting is actually air or the atmosphere. See, this is why we modulate our signals, for them to have different frequencies. Each signal is having different frequency, i.e. signal is modulated to a different carrier frequency. This is the principle of modulation. Channels are separated by the strips of unused bandwidth called guard bands to prevent overlapping. Guard bands acts as some kind of a buffer between adjacent frequencies to make sure no interference will happen between them. This is an illustration for frequency division multiplexing. We have three pairs of telephone, with each pair talking to each other or communicating with each other. A single path can be used, which are divided by channels 1, 2, and 3, but a multiplexer is needed to actually separate the frequencies of the three telephone wires. So in terms of frequency, we can see that the path is divided into different channels, each of which have frequencies that aren't overlapping. And for purposes of avoiding interferences, guard bands are used. These are applications of FDM. FDM is used for FM and AM radio broadcasting. AM frequencies range from 525 to 1700 kHz. FM frequencies are from 88 to 108 MHz. FDM is used in television broadcasting. And also, first generation cellular telephone uses FDM. This is an illustration of FDM in the transmitter side. As you can see, again, we'll use the example of telephones. The input for these telephones are voice signals. The telephones allot frequencies from 0 to 4 kHz as the bandwidth. To make sure that the message signals from each telephone do not interfere with each other, a modulation process takes place. In the first telephone, a frequency of F1 acts as the carrier frequency to modulate the voice signal. So it's a relatively low frequency compared to F2 and F3, but it's actually a high frequency signal compared to the original voice signal. The same thing with the second telephone, it is modulated by F2, and lastly, for the third telephone, it is modulated by F3, which is the highest frequency of all the carriers. And then the signals will then be placed into a linear mixer, which acts as the multiplexer that combines all the three signals into one output. And as you can see, the single output is undiscernible by human eyes. It is the combination of three signals after all. If we look at FDM in the frequency domain, it actually looks pretty similar to the time domain. But now you can see clearly that frequencies F1, F2, and F3 are far apart, so they do not interfere with each other. And in the channel, it is clear that all the frequencies have guard band between them to make sure that interference will not occur. This is an example of FDM. This is the frequency bands for FM station. It goes from 88 all the way to 108 megahertz. So as you can see, each channel is 200 kilohertz wide with a carrier frequency in the center of the bandwidth. And then between channels, there is no station to ensure that there is sufficient space between the channels to act as guard bands. This is FDM in the demultiplexer side. As you can see, the input of the demultiplexer is the output of our multiplexer. The demultiplexer basically separates the signal via the filter, which is tuned to only allow certain frequencies to pass through. So for our first filter, the topmost filter, it will allow the relatively low frequency signal to pass through, and then a demodulator circuit will process the signal, and the output of the demodulator is the original message signal. For the second filter, it will allow the corresponding signal to pass through, which will then pass through a demodulator, and the output will again be the original message signal for the second telephone. And lastly, the third filter will allow the highest frequency of the three to pass through, and again this signal will pass through a demodulator, which will only allow the original message signal to get to the third telephone. And for the demultiplexer frequency domain, we have the input of our demultiplexer as the output of our multiplexer, and we can see that the three signal bandwidths do not overlap each other. The three will pass through their respective filters, and then each signal will pass through a demultiplexer to output only the baseband or the original message signal. Let's take a look at an example problem. 5 channels each with 100 kHz bandwidth are to be multiplexed together. What is the minimum bandwidth of the link if there is a need for a guard band of 10 kHz between the channels to prevent interference? Now for our solution, for 5 channels, we need at least 4 guard bands between each channel. This means that the required bandwidth is at least 5. This is for 5 channels times 100 kHz. It's because 100 kHz are required for one channel plus 4 guard bands times 10 kHz equals 540 kHz. So 540 kHz is the total minimum bandwidth for the entire system. Analog carrier systems. AT&T in the USA, this is the hierarchy of FDM schemes. For A group, it is composed of 12 voice channels, 4 kHz each, which gives a total of 48 kHz of bandwidth. This ranges from 60 kHz up to 108 kHz. For supergroup, it is composed of 60 channels, FDM of 5 group signals on carriers between 420 and 612 kHz. And lastly, for the master group, it is composed of 10 supergroups. This is the illustration. First, we have our 12 voice channels. It will be multiplexed and combined into one signal. This is our 48 kHz 12 voice channels. And then 5 of these groups will further be multiplexed to combine into one supergroup, which in turn is now 240 kHz, and it has 60 voice channels. 10 supergroups will combine to form a master group. It now has 2.52 megahertz of bandwidth. It is composed of 600 voice channels. And lastly, 6 master groups will combine through a multiplexer to form a jumbo group, which is 16.984 megahertz, and it is now composed of 3,600 voice channels. So you have to remember this. First, we have group composed of 12 voice channels. Then we have supergroup. It is composed of 60 voice channels or 5 groups. Next, we have master group. It has 600 voice channels. It is composed of 10 supergroups. And the largest one is the jumbo group, which is composed of 6 master groups, and it has 3,600 voice channels. Wavelength division multiplexing. Wavelength division multiplexing works the same way as FDM because wavelength and frequency are like opposite sides of the same coin. They're both related by the speed of which the signal is transferred. In this case, the speed of the signal is the speed of light. Different optical signals or light signals are transmitted through optical fiber. Various light waves from different sources are combined to form a composite light signal that is transmitted across the channel to the receiver. Keep in mind that wavelength division multiplexing is an analog technique. At the receiver side, this composite light signal is broken into different light waves by a demultiplexer. This combining and splitting of light waves is done by using a prism. A prism bends beams of light based on the angle of incidence and the frequency of light wave. This illustrates how wavelength division multiplexing works. First, we have three wavelengths on the input side of a multiplexer. In this example, we have red, green, and something that looks like a dark red color. It will pass through a multiplexer, which would then combine these three colors and send it via a fiber optic cable. In the fiber optic cable, we can see that the three original light waves are combined into a single light wave. So we have lambda 1 plus lambda 2 plus lambda 3. And it will serve as the input of our demultiplexer. The multiplexer would then do the reverse of the multiplexer, which is to separate these three light signals into the three different wavelengths. So we have our red, green, and dark red back as our message signal again. WDM multiplexes multiple beams of light that must be at different frequencies. These are carried by optical fibers, which acts as the transmission medium for light. Each color of light corresponds for a wavelength, carries separate data channel or separate message signals. It is first developed in 1997 in Bell Labs, in which there are 100 beams, each at 10 gigabits per second, giving 1 terabit per second of speed. So this is much faster than our wired transfer of message. Commercial systems of 160 channels of 10 gigabits per second are now available. Lab systems or Alcatel has 256 channels at 39.8 gigabits per second each that can reach a total bit transfer speed of 10.1 terabits per second over 100 kilometers. WDM operation. It operates in the same general architecture as other FDM. Number of sources generating laser beams at different frequencies. The multiplexer consolidates sources for transmission over a single fiber. Optical amplifiers amplify all wavelengths. These are typically tens of kilometers apart. And take note that light waves generally suffer less attenuation compared to electrical signals. So we can have less amplifiers using fiber optic cables than when using wired copper cables. The demultiplexer separates channels at the destination. These are mostly 15 nanometer wavelength range. The previous bandwidth was 200 megahertz per channel. Now it's up to 50 gigahertz and still increasing, depending on the application. Time division multiplexing. Channel or link is not divided on the basis of frequency, but on the basis of time. Total time available in the channel is divided between several users. Each user is allotted a particular time interval called time slot or slice. In TDM, the data rate capacity of the transmission medium should be greater than the data rate required by the sending or receiving devices. And you must remember that TDM is a digital multiplexing technique. This is an illustration of how TDM works. On the input side, we have 4 devices. The 4 devices will transmit individual messages that will pass through a multiplexer. Instead of combining the 4 messages, as the multiplexer did in FDM and WDM. This time, the multiplexer will allot a time slot for each of the message signal. So it will allow the entire message signal to pass through the channel one at a time. In this case, it allowed the message signal from device 1 to pass through, and then from device 2, and then from device 3, and then from device 4. After that, it reverts back to device 1, and then to device 2, and then to device 3, and then to device 4, and so on, until all of them have transmitted their respective message signals. The demultiplexer will then be responsible of distributing which message signal will go to which device. This is another illustration of TDM. As you can see, for the entire time, one channel at a time, or one message signal at a time can pass through, and the message signal that can pass through can consume the entire bandwidth of the path or the channel. Synchronous TDM. Each device is given the same time slot to transmit the data over the link, whether the device has any data to transmit or not. Each device places its data onto the link when its time slot arrives. Each device is given the possession of line turn by turn. If any device does not have data to send, then its time slot remains empty. Time slots are organized into frames, and each frame consists of one or more time slots. If there are n sending devices, there will be n slots in the frame. So this is how it works. For example, we have 5 inputs from 5 devices. The multiplexer will chop each input, divide them into frame. So in a single frame, a message from device 1 until device 5 is present. Multiplexing process of STDM. Every device is given the opportunity to transmit a specific amount of data onto the link. Each device gets its turn in fixed order and for a fixed amount of time. This is the interleaving. Interleaving is done by a character or 1 byte. Each frame consists of 4 slots, as there are 4 input devices. In our previous example, there are 5 input devices, so there were 5 slots. And then slots of some devices go empty if they do not have any data to send. This may be an actual operation of a synchronous TDM. As we can see, there are 4 devices, so there are 4 inputs. Input A transmits a message all of the time. Input B only transmits a message very seldom. And then input C transmits more message than input B. And lastly, input D transmits more message than input C but less than input A. So the multiplexer, depicted here by an arrow that is rotating and connects to one wire at a time. So first it connects to wire A and then B, then rotates to wire C and lastly to D before going back again to A. And the output, as you can see, the first output we have in the rightmost side. From the right, it goes A, B, C, D. So as you can see, the rotation of the arrow is counterclockwise. And then next, A, B, C, D, and next A, B, C, D again. And then this is interesting. For the fourth message, it goes A blank C, D. This is because input B only transmitted 3 messages. So its time slot remained blank for this particular frame. And then A blank blank D as input C did not transmit any message as well for this specific frame. And for our last frame, we only have input A because A is the only one that transmitted a message for this frame. And onto the receiving side, we have a demultiplexer, which is again depicted by an arrowhead, this time rotating clockwise, to give the proper message to the proper recipient. So for message A, the recipient will be device A, and then for message B, the recipient will be device B, and so on. Framing bits for synchronous time division multiplexing technique. We have a synchronization pattern. So in every frame, a bit is added just to indicate that this is the start of the frame. So first we have 1, and then for the second frame we have bit 0, for the third frame we have again bit 1, and then for the third frame bit 0, and so on. This is the synchronization pattern. This is just to tell the multiplexer that a new frame has arrived. Now, asynchronous TDM or ASTDM, also known as statistical time division multiplexing, in this, time slots are not fixed, i.e. slots are flexible. Total speed of the input lines can be greater than the capacity of the path. With n input lines and m slots, i.e. m less than n, slots are not predefined. Rather, slots are allocated to any of the device that has data to send. Let's take a look at this illustration. So as you can see, there are 5 inputs. But in each frame, there are only 3 slots. This works in the assumption that not all inputs or not all devices will send a message. Interleaving. The process of taking a group of bits from each input line for multiplexing is called interleaving. We interleave bits 1 minus n from each input onto one output. Synchronization. To ensure that the receiver correctly reads the incoming bits, i.e. knows that the incoming bit boundaries to interpret a 1 and a 0, a known bit pattern is used between the frames. The receiver looks for the anticipated bit and starts counting bits until the end of the frame. Then it starts over again with the reception of another known bit or expected bit. These bits, or bit patterns, are called synchronization bits. They are part of the overhead of the transmission. So again, this is another example. We have our synchronization pattern 101. So a synchronization bit is sent in front of the frame. And that's it for multiplexing.